Tonight, we're going to answer a question that sounds trivial and turns out to be one of the most profound in the history of science. The question is this: why is space dark? You might be tempted to laugh that off. Space is dark because it's space. That's just what space is. It's the void, the vacuum, the emptiness between things. Of course it's dark. What else would it be? And yet, the moment you sit with that answer seriously, it starts to fall apart. The universe contains somewhere between 100 billion and 2 trillion galaxies. Each of those galaxies contains somewhere between 100 million and 1 trillion stars. The total number of stars in the observable universe is estimated at somewhere around 100,000 billion, a number so large that writing it out in full would take several pages. Every one of those stars is a nuclear furnace radiating light in all directions, continuously, for millions to billions of years. In a universe with that many sources of light distributed through space in every direction, you could point a telescope. Why is the sky between the stars black? Why don't all those photons from all those stars and all those galaxies add up to a sky that glows continuously, uniformly, brilliantly? Why can you look between the stars and see darkness at all, rather than a surface of pure blinding light in every direction you choose to look? This is not a frivolous question dressed up to sound deep. It is a genuinely deep question that some of the greatest minds in the history of physics have wrestled with, and the answer leads directly to the most important cosmological discoveries of the last 2 centuries. The darkness of the night sky is evidence of the Big Bang. It is evidence of the finite age of the universe. It is evidence of cosmic expansion. It encodes the entire history of the cosmos. And once you know how to read it, the darkness stops being absence and starts being information. The answer involves light that has been traveling for nearly 14 billion years and hasn't reached us yet. It involves light that set out toward us long ago from stars that no longer exist, from the direction of regions so distant that the universe's expansion is carrying them away faster than any light can follow. It involves the discovery of a background radiation that fills the entire sky at a temperature barely above absolute zero, the cooled and stretched remnant of the universe's earliest light. And it involves the physics of how the universe can contain vastly more light than we can see, most of it transformed by the expansion of space into wavelengths too long for human eyes or even most instruments to detect. By the end of tonight, the darkness of the night sky will not seem empty to you. It will seem full of information, full of history, full of physics that took centuries to work out, and that touches the deepest questions about what the universe is, how old it is, where it came from, and where it is going. If this kind of deep journey into a seemingly simple question is what brings you here, subscribe and leave a like. It helps this channel reach more people who want the complete version of the answers, rather than the superficial one. Now, let us begin with a question that troubled astronomers for hundreds of years, and that has a name. The history of how this question was answered is itself remarkable. The problem of the dark night sky was taken seriously by astronomers from the Renaissance onward, but its resolution required discoveries that came only in the 20th century. The discovery that the universe is expanding, confirmed by Edwin Hubble in 1929. The discovery of the cosmic microwave background, made accidentally by Penzias and Wilson in 1964. And the discovery that the expansion of the universe is accelerating, announced in 1998. Each of these discoveries was separately Nobel Prize-worthy and separately transformative for cosmology, and all of them are required in combination to answer why the sky is dark. The darkness of the night sky, it turns out, is one of the most information-rich observations in the history of astronomy. It simultaneously encodes the age of the universe, the fact of its expansion, the nature of dark energy, the existence of a cosmic event horizon, and the specific chemical and thermal conditions that allow planets like Earth to exist. Unpacking what the darkness means, carefully and completely, is a journey through the most fundamental questions cosmology has ever asked. There is also something to be said about the methodology here. This is a case where a purely observational fact, the simple act of looking up at night and noticing that the sky between the stars is dark, turns out to contain within it an enormous amount of physical information. No specialized equipment was needed to make the observation. Every human who has ever looked at the night sky has observed the key evidence for the Big Bang without knowing it. The evidence was hiding in plain sight, in the dark, for all of human history. The question of why the night sky is dark has been formally posed in one form or another since the early Renaissance, but it is most associated with a German physician and amateur astronomer named Heinrich Wilhelm Olbers, who articulated it clearly in 1823 in a paper on comets. The problem he described has been called Olbers Paradox ever since. Though in the tradition of scientific naming, that doesn't always give credit to the original discoverers, it was discussed earlier by the English astronomer Thomas Digges in 1576, by Johannes Kepler in 1610, and in more mathematical detail by the Swiss astronomer Jean-Philippe Loewe de Chézeaux in 1744. What Olbers did was state the problem with a clarity that made it impossible to dismiss. The argument in its essence is this: assume the universe is infinite in extent, and assume that it contains stars distributed more or less uniformly throughout that infinite space. If you look in any direction, your line of sight must eventually hit a star. In an infinite universe with uniform stellar distribution, every line of sight intersects a stellar surface somewhere, no matter the direction. The sky should therefore be entirely covered by stars, wall-to-wall stellar surfaces in every direction. And since those stars collectively emit light in all directions, the sky should glow at the surface temperature of a typical stellar photosphere, roughly as bright as the surface of the sun. This obviously does not describe the sky we observe, but the dissonance between the argument and the observation was not easy to resolve for the thinkers of the time, because each premise of the argument seemed individually unassailable. The universe being infinite was not just an assumption, it was the dominant cosmological belief, built on the logic that any finite universe would imply a boundary. And a boundary implies something beyond the boundary, which contradicts the idea of the universe as everything that exists. Infinity seemed like the only logically consistent option. The assumption that stars are distributed uniformly through this infinite space was supported by everything astronomers of the era could observe. Look in different directions, and you see stars in every direction. No direction shows an obviously empty quarter of the sky from which stars are absent. Uniformity seemed observationally justified. The assumption that light propagates through space without significant absorption or loss was also well-grounded. If you propose that dust or gas between the stars absorbs the light and prevents it from reaching us, the argument simply shifts. That dust or gas would itself absorb so much light that it would heat up and eventually re-radiate, reaching thermal equilibrium with the stars. You cannot resolve the paradox by inserting an absorber, because the absorber itself must eventually glow. So, the paradox sat, a genuine logical puzzle with no obvious resolution, for about a century after Olbers restated it. The resolution required new cosmology. Thomas Digges, writing in 1576, was among the first to grapple with the implication of an infinite universe containing stars. He populated his infinite space with stars and noted that they should collectively illuminate everything. Kepler, confronting the same problem in 1610 in response to Giordano Bruno's advocacy of an infinite universe, argued that the darkness of the night sky was evidence that the universe must be finite. If it were infinite and uniformly filled with stars, he reasoned, the sky would be too bright. This is perhaps the earliest clear statement of what would become Olbers' paradox, and it is remarkable that Kepler had the correct logical chain, even if he didn't have the tools to complete the resolution. The reason the problem is called Olbers' paradox rather than Digges's, or Kepler's, or Chézeaux's is partly historical accident, partly the fact that Olbers' 1823 formulation reached a wide scientific audience, and partly the influence of Edgar Allan Poe, who in his 1848 cosmological prose poem Eureka described essentially the correct resolution of the paradox, suggesting that the darkness of the night sky indicated the universe had not existed long enough for light from all stars to have reached us. Poe, who was not a scientist, arrived through poetic intuition at an answer that professional astronomers would not confirm for another century. The cultural dimension of the paradox is also worth noting. The question of whether the universe is infinite was not merely a technical astronomical question in the 17th and 18th centuries. It had deep philosophical and theological implications. An infinite universe with no center challenged the Aristotelian and medieval cosmological framework of a finite celestial sphere. The darkness of the night sky was, in this context, cosmologically charged evidence that something was wrong with the dominant worldview. To feel the full force of the problem, it is worth working through the quantitative argument more carefully, because the argument does not merely suggest that the sky would be somewhat brighter than it is. It suggests the sky would be completely covered in light of the same intensity as a stellar surface. The key is the inverse square law. Light from a star at distance d is spread over a sphere of surface area proportional to d squared. So the apparent brightness of any individual star falls as 1 over d squared. At twice the distance, a star is 1/4 as bright. This is why distant stars look faint. But the number of stars within a thin shell of space at distance d and thickness td scales as d squared times t day. The number of stars grows as the square of the distance. When you multiply the number of stars at distance d by the apparent brightness of each one, the 2d squared factors cancel exactly. The contribution to the sky brightness from stars in a thin shell is independent of how far away the shell is. This is the heart of the paradox. In an infinite universe, you are summing up equal contributions from shells at every possible distance, all the way to infinity. The sum has no upper limit. Even if each distant shell's stars are individually faint, there are more of them in exact proportion, and the total brightness from that shell is the same as from any other shell. Add infinitely many equal contributions, and you get infinite sky brightness. In practice, the argument doesn't produce truly infinite brightness, because the apparent sizes of stars also matter. Stars subtend small but finite angles in the sky. Eventually, closer stars block the light from more distant ones, the same way that in a forest you can only see to the nearest trees. The end point is a sky completely tiled by stellar surfaces, uniformly bright, with every point in the sky glowing as brightly as the surface of a typical star. The predicted temperature of the sky from this argument is several thousand Kelvin. The actual night sky, away from the Milky Way and away from bright stars, has a surface brightness many orders of magnitude below this prediction. The observed brightness is roughly a factor of 10 to the 23rd power, less than an infinite static universe sky should produce. The paradox is not a subtle discrepancy. It is a discrepancy of about 23 orders of magnitude. The sky is not just slightly dimmer than expected, it is incomprehensibly dimmer. Something is fundamentally wrong with at least one of the premises, and it is the resolution of which premise is wrong that makes this problem scientifically productive. There is a useful way to visualize the argument using a forest analogy. Imagine standing in a forest where trees are distributed randomly in all directions with uniform density. In any direction you look, your line of sight will eventually hit a tree trunk. If the forest is large enough and the tree density is high enough, there is no direction you could look and see clear sky. Every sight line terminates at a tree. The forest looks solid in every direction. The same argument applies to stars in an infinite universe. No matter how far apart the stars are, if the universe is infinite, every line of sight eventually hits a star. The quantitative version of the argument addresses the objection that distant stars are so faint they might not matter. The inverse square law of brightness is exactly countered by the quadratic increase in the number of stars at a given distance. The contribution to sky brightness from a shell of stars at distance d is the product of the number of stars in that shell, proportional to d squared, and the apparent brightness of each star proportional to 1 over d squared. The d squared factors cancel, and every shell contributes equally to the sky brightness. Sum over infinitely many shells, and you get infinite brightness. The faintness of distant stars does not save you from the paradox because there are proportionally more of them. This mathematical equivalence between star number and brightness falloff is not obvious intuitively, which is part of why the paradox took so long to be clearly stated. It requires the specific relationship between volume and distance, which grows as d cubed for a spherical shell of constant thickness, d, divided by the surface area of the sphere at that distance, which grows as d squared, with the result being a linear growth in number with dA. That exactly compensates the inverse square brightness falloff. The resolution of Olbers' paradox that is most often stated first in textbooks involves the finite age of the universe. If the universe has existed for only a finite amount of time, then there is a finite amount of time during which stars have been shining and producing light. Light from stars travels at the speed of light. In a universe that has existed for approximately 13.8 billion years, light produced at the beginning of stellar activity has had, at most, about 13 billion years to travel. Anything beyond about 13 billion light years is simply not yet visible to us, because no light from that distance has had time to arrive. This argument is correct and important, but it is not the complete resolution. It does a certain amount of work in understanding why we see darkness, but by itself, it is insufficient. Here is why. In an infinite universe of finite age, the stars we cannot yet see because their light hasn't reached us don't contribute to sky brightness. But the stars we can see within the observable horizon still number in the hundreds of billions. Even considering only the light from stars within the observable universe, the sky should be significantly brighter than it is. The finite age of the universe limits the number of shells contributing to sky brightness, but the remaining shells within the observable universe still contain enough stars that the brightness should be detectable as a significant, uniform glow covering the entire sky. Moreover, the finite age argument alone doesn't account for the specific distribution of what we observe. The sky isn't uniformly bright at a low level. It has specific bright sources, the stars and galaxies, and dark regions between them. If the missing light were simply the light from beyond our horizon that hasn't arrived yet, we would still expect a significant diffuse glow from all the stars within the horizon. The glow isn't there in any visible form. Something else is suppressing the light. That something else is the expansion of the universe, and its effect on light is transformative in a way that required the full development of general relativity and observational cosmology to understand properly. The finite age argument is real and matters, but it is only part of the answer. The specific contribution of finite age to the resolution of Olbers' paradox can be quantified. In the 13.8 billion years since the Big Bang, the universe has contained stars for roughly 13.6 billion years, since the first stars formed about 200 million years after the Big Bang. Light from a star 13.6 billion light-years away has had just enough time to reach us. Stars beyond that distance have been shining for the same amount of time, but their light has not yet arrived. However, computing the sky brightness from all stars within 13.6 billion light-years, using Olbers' logic, gives a result that is still many orders of magnitude brighter than what we observe. This tells us that finite age alone cannot explain the observed darkness. The visible sky from stars within our light horizon should still be significantly brighter than it is. The discrepancy between this calculation and observation requires additional physics, specifically the expansion of the universe and the resulting redshift. The physicist Edwin Hubble, who wrote a landmark book on Olbers' Paradox in 1987 called Darkness at Night, showed through careful calculation that the finite age argument accounts for only a small fraction of the total resolution. The dominant factor, by a large margin, is the expansion of the universe and the redshift it produces. If the universe were finite in age but not expanding, the sky would be much brighter than we observe, though not as bright as the full Olbers prediction. The expansion is doing the heavy lifting in explaining the darkness, and finite age is a secondary contributor, important but not dominant. The distinction matters because it clarifies what the darkness is actually telling us. It is not primarily telling us that the universe is young, though that is true. It is primarily telling us that the universe is expanding, and that the expansion has been going on for long enough to redshift most of the light from distant sources out of the visible spectrum. There is a further subtlety worth naming. The question is sometimes posed as, would the sky be bright if the universe were infinite, but we could only see a finite portion of it due to its age? The answer depends on what portion is visible. For a 13 billion-year-old universe, the visible portion contains enough stars that their collective brightness, without redshift, would still be substantially brighter than the sky we observe. The finite age argument reduces the brightness by the ratio of the observable volume to the infinite volume predicted by Olbers' model. But this ratio, while very large, is not large enough to fully explain the observed darkness. The redshift from expansion must be invoked as well. In 1929, Edwin Hubble published his measurement showing that distant galaxies are receding from us, and that the speed of recession increases proportionally with distance. This was the observational confirmation of what Einstein's theory of general relativity had predicted, and what Alexander Friedmann and Georges Lemaitre had worked out theoretically. The universe is expanding. The space between galaxies is not static, it is growing. The implications of expansion for the resolution of Olbers Paradox are profound and, once understood, completely change the picture. When light travels through expanding space, something happens to it. The space it is traveling through is stretching while the light is in transit. This stretching affects the light's wavelength. A photon of visible light that starts its journey with a wavelength appropriate for red light, say 700 nanometers, will arrive with a longer wavelength if the space it traveled through expanded during the journey. The expansion stretches the wavelength of the photon, shifting it toward longer wavelengths. This is the cosmic redshift, and it means that light from distant sources arrives at our telescopes with less energy per photon than it had when emitted. The amount of redshift tells us how much the universe has expanded since the light was emitted. A galaxy with a redshift of 1, meaning its light has been stretched to twice the original wavelength, emitted that light when the universe was half its current size. A galaxy with a redshift of 10 emitted its light when the universe was 1/11th its current size. The most distant objects we can observe, with redshifts above 10, emitted their light when the universe was a tiny fraction of its current size. For Olbers' paradox, the critical consequence is energy loss. Every photon arriving from a distant galaxy has been redshifted, meaning it carries less energy than when emitted. The relationship between redshift and energy loss is direct. A photon redshifted by a factor of 2 arrives with half the energy it had at emission. Stars in the early universe, receding from us at high speeds because the universe was expanding rapidly, emitted light that has been heavily redshifted. The photons that arrive from those stars carry a small fraction of the energy they carried at emission. This is a major part of why the sky is dark. The most distant stars and galaxies, which in a static universe would contribute the same sky brightness as nearby ones, have their light redshifted so severely that it arrives carrying only a tiny fraction of its original energy. Much of the light from distant stars and the early universe has been shifted out of the visible spectrum entirely into infrared and microwave wavelengths invisible to the naked eye. The visible sky is dark, not because the light isn't arriving, but because most of it has arrived in forms we cannot see. The concept of cosmic redshift is sometimes confused with the Doppler effect, the shift in sound or light frequency produced when a source is moving relative to an observer. A receding ambulance has a lower pitch siren than an approaching one because the sound waves are stretched by the relative motion. The cosmic redshift looks similar in its effects, but has a different physical origin. The galaxies are not moving through space at high speed away from us, in the way a receding ambulance moves away. Rather, the space between us and the galaxies is expanding, stretching the photons in transit along with the space itself. The practical distinction matters because the rate at which distant galaxies appear to recede can exceed the speed of light without violating special relativity. Special relativity forbids objects from moving through space faster than light, but it does not forbid space itself from expanding at any rate. Galaxies beyond a certain distance are being carried away from us faster than light can cross the growing gap between us. Their light is currently making no net progress toward us. Yet, we can still see light from even more distant objects, because that light was emitted when those objects were much closer, before the expansion had grown so large. The energy loss from cosmological redshift is not a small effect for distant sources. A galaxy at a redshift of 5 has had its light wavelength stretched by a factor of 6 since emission. The energy of each photon is inversely proportional to wavelength, so each photon arrives with 1/6 the energy it had at emission. A galaxy at redshift 10 has photons arriving with 1/11 their original energy. The most distant objects in the universe have had their photons reduced to tiny fractions of their original energy by this stretching. This is why the sky is dark, not because stars don't emit enough light, but because the photons from distant stars arrive with almost none of their original energy. Most of it deposited into the expansion of space itself. Here is something remarkable. The night sky is not actually dark. In one very specific and very important sense, the sky is glowing brilliantly in every direction simultaneously, bathed in the most ancient light in the observable universe. You cannot see it with your eyes. You cannot detect it with a visible light camera, but if you could see in microwaves, the sky would glow uniformly from every direction with a brightness corresponding to a temperature of 2.725 Kelvin, just a fraction above absolute zero. This is the cosmic microwave background discovered accidentally in 1964 by Arno Penzias and Robert Wilson at Bell Labs, who noticed that their microwave antenna had an annoying and inexplicable noise that came equally from every direction of the sky regardless of where they pointed. The noise didn't go away at night. It didn't change with the seasons. It didn't correspond to any known radio source. It was everywhere, isotropic and constant. And it was the single most important accidental discovery in the history of observational cosmology. What Penzias and Wilson had found was the cooled, redshifted remnant of the light from the Big Bang itself, or more precisely, from the moment about 380,000 years after the Big Bang when the universe first became transparent to light. Before that moment, the universe was a hot, dense plasma in which photons were continuously absorbed and re-emitted, unable to travel any significant distance. When the universe cooled enough for electrons to combine with protons and form neutral hydrogen atoms, the photons were suddenly free to travel, and they have been doing so ever since, for about 13.4 billion years. The light released at that moment of recombination had a temperature of about 3,000 Kelvin, similar to a dim reddish star's surface. As the universe has expanded by a factor of about 1,100 since then, that light has been redshifted by the same factor, cooling from 3,000 Kelvin to 2.725 Kelvin. The photons are now in the microwave part of the spectrum, rather than visible light, but they are still there, still filling the universe in every direction with equal intensity. The cosmic microwave background is the direct answer to Olbers' paradox in one sense. The universe does have a background glow filling every direction. It is just at a temperature so cold that its peak emission is in the microwave, not the visible. The vast stretching of the universe's expansion has cooled what was once a blinding plasma to something barely warmer than absolute zero. The background is real. The darkness is the stretched, cooled version of what was once brilliant light from the universe's earliest accessible moments. The uniformity of the cosmic microwave background across the sky is extraordinary. The temperature is 2.725 Kelvin in every direction, with fluctuations at the level of only 1 part in 100,000. These tiny fluctuations, mapped in extraordinary detail by the COBE, WMAP, and Planck satellites over the past 3 decades, are the seeds from which all cosmic structure grew. Slightly denser regions in the early universe had slightly higher temperatures in the CMB. Those denser regions were where gravity was strongest, where matter clumped first, where the first galaxies formed. The pattern of temperature fluctuations in the microwave background is literally a map of the initial conditions that led to every galaxy, every star, every planet in the observable universe. The fact that the CMB exists at all is a direct confirmation of the Big Bang model. It was predicted by George Gamow, Ralph Alpher, and Robert Herman in the 1940s as a consequence of a hot, dense early universe, and its 1964 discovery was immediately recognized as confirmation of the Big Bang over the competing steady-state model. The specific temperature of 2.725 Kelvin and the black-body spectrum of the radiation match the Big Bang predictions precisely. The CMB is also a practical answer to Olbers' paradox in the following sense. The paradox asks why the sky is dark, but the CMB demonstrates that the sky is not dark at all in the microwave. The entire sky is glowing uniformly, everywhere you look, with the radiation from the Big Bang. This glow has a precise temperature and a precise spectrum that have been measured to extraordinary accuracy. The universe is literally filled with light from its own beginning. That light just happens to be invisible to human eyes. To understand why space is dark, it helps to be precise about what darkness actually means in a physical sense. Darkness is not the absence of matter. It is not the absence of electromagnetic radiation. In the context of the night sky, darkness means the absence of photons in the wavelengths detectable by human eyes, roughly 380 to 740 nanometers. Outside that narrow window, space is anything but dark. The electromagnetic spectrum is vast. Radio waves span wavelengths from meters to kilometers. Microwaves, which include the cosmic background radiation, span millimeters to centimeters. Infrared light, which is emitted by anything with warmth, spans from hundreds of micrometers down to the edge of visible red. Ultraviolet light spans from the edge of visible violet to about 10 nanometers. X-rays go shorter still, down to fractions of a nanometer. Gamma rays are shorter yet. Every one of these bands of the electromagnetic spectrum has its own sky, and most of those skies are not dark. The radio sky is filled with synchrotron emission from energetic electrons spiraling in magnetic fields across the galaxy, with the thermal emission of cold gas clouds, and with the cosmic microwave background at the long wavelength end. The infrared sky is bright with the emission of dust heated by stars, of cool stars themselves, and of galaxies at moderate redshift, whose visible light has been shifted into infrared. The X-ray sky blazes with emission from hot gas in galaxy clusters, from black hole accretion disks, and from binary star systems where matter is falling onto compact objects. The gamma-ray sky sparkles with millisecond pulsar flashes, with the afterglows of distant gamma-ray bursts, and with the annihilation of matter and antimatter. When we say the sky is dark, we are making a statement about a specific biological limitation of the observer, not a statement about the universe itself. The universe is not dark. It is electromagnetic activity across dozens of orders of magnitude of wavelength, happening everywhere simultaneously, producing a complex and rich electromagnetic environment at every point in space. We simply can only detect a narrow slice of it without instruments, and that narrow slice, the visible, happens to be the slice where the darkness is most apparent. Understanding this reframes the whole problem. Why is space dark is really the question. Why is the universe not particularly bright, specifically in the narrow band of electromagnetic radiation that human vision evolved to detect? And the answer is that the universe's electromagnetic output at any given point is mostly in wavelengths outside that narrow band, for reasons that are deeply connected to the age and expansion history of the cosmos. The human eye evolved in a specific environment to respond to a specific range of electromagnetic frequencies. The primary driver of this evolution was the availability of sunlight, which has a spectrum peaking in the visible range because the sun's surface temperature of about 5,778 Kelvin corresponds to peak emission at visible wavelengths. Eyes that could detect the most abundant photons in the environment were more useful. So, evolution pushed towards sensitivity in the 380 to 740 nanometer range. Other organisms have evolved sensitivity to different ranges. Many insects see in the ultraviolet, which is useful for identifying flowers that have ultraviolet reflectance patterns invisible to human eyes. Pit vipers and some other reptiles have infrared sensing organs that allow them to detect the thermal radiation of warm-bodied prey. The range of electromagnetic radiation that constitutes darkness for one organism may be bright and information-rich for another. From the perspective of a microwave-sensitive organism or instrument, the entire universe is uniformly lit with the cosmic microwave background. Not brightly lit, since 2.72, Kelvin is very cold, but uniformly and isotropically illuminated with no dark regions anywhere. From the perspective of an infrared observer, the universe is full of faint glows from cool dust and cold gas in and around galaxies. From the perspective of an X-ray observatory, active galactic nuclei and galaxy cluster gas provide bright point sources against a diffuse background. The universe is layered with electromagnetic information across all wavelengths, and any statement about darkness is always a statement about a specific wavelength window and a specific level of sensitivity. The fact that the visible universe appears dark to human eyes is therefore a statement about the specific properties of human vision in relation to the specific state of the universe in our cosmic epoch. At an earlier time, when the universe was hotter and more compact, even human eyes would have seen a bright sky. In the far future, when even the microwave background has been cooled to invisibility by further expansion, every wavelength range will be dark. The observable universe is not the same as the universe. The universe, as best current cosmology can determine, extends without known limit in every direction, potentially infinite in spatial extent. The observable universe is the subset of all that space from which light has had time to reach us in the 13.8 billion years since the Big Bang. Because light travels at a finite speed and the universe has a finite age, there is a maximum distance from which any signal could have reached us: the particle horizon. The current distance to our particle horizon, accounting for the expansion of space during the journey of the light, is approximately 46 billion light-years in every direction, giving the observable universe a total diameter of about 93 billion light-years. This is larger than 13.8 billion light-years, precisely because space has been expanding while the light was in transit. The regions that emitted the oldest light we can see have been carried much farther from us in the time since they emitted it. Within this 93 billion light-year sphere sit approximately 2 trillion galaxies, each containing hundreds of billions to trillions of stars. This is an enormous amount of light-producing matter, and it should contribute significantly to sky brightness. The reason it doesn't is the combination of factors already discussed: the finite time during which those stars have been producing light, the redshifting of that light by the expansion of space, and the fact that even within the observable universe, most of the light from distant stars has been stretched to non-visible wavelengths. But the existence of the particle horizon has another implication for the darkness question that is worth stating explicitly. Beyond our particle horizon, Stars and galaxies exist, presumably in similar abundance to what we observe within it. Those stars are producing light right now. But that light will never reach us, not because of any limitation in our technology, but because the space between us and those regions is expanding faster than light can cross it. The expansion of the universe has separated us from those regions causally. We can never receive information from them, and they can never receive information from us. We are in permanently separate causal regions. The darkness between us and those sources is therefore not temporary darkness that will eventually be illuminated as their light arrives. It is permanent darkness. Those stars' light is racing toward us, but losing ground as the space between expands. We are in an expanding bubble of the observable universe surrounded by a sea of stars and galaxies whose light is permanently outrun by the expansion. The darkness beyond the horizon is not night waiting for dawn. It is a permanent condition of our location in an expanding universe. The mathematics of the particle horizon involves a subtlety that trips up many initial encounters with cosmology. The horizon is not simply at a distance of 13.8 billion light years, because light has been traveling for 13.8 billion years. The expansion of space during the journey of the light changes the calculation. A photon that was emitted when the universe was very young started out close to us by the standards of that time, but as it traveled, the space behind it expanded. The region that emitted that ancient photon is now much farther from us than the photon's travel time in years might suggest. The proper calculation, integrating the expansion history of the universe, gives a particle horizon of about 46 billion light years. This means we can receive light from objects that are now 46 billion light years away, even though the universe is only 13.8 billion years old, because those objects were much closer to us when they emitted the light we receive. The universe has grown by roughly a factor of 1,100 since the emission of the oldest light we can detect, the cosmic microwave background. The particle horizon grows with time. As more time passes since the Big Bang, the sphere of space from which light can have reached us expands. New regions of the universe come into view as we receive light from progressively greater distances. In principle, future observers billions of years from now could receive light from regions currently beyond our particle horizon. However, the accelerating expansion of the universe works against this in an important way. While the particle horizon continues to grow, the fraction of the universe's total volume it encompasses grows more slowly than the total universe, and the cosmic event horizon, the sphere beyond which we can never send information or hope to receive future light, is actually shrinking in proper distance terms due to the accelerating expansion. The darkness of space has a dimension beyond the absence of light, because space is permeated by forms of matter that neither emit nor absorb nor reflect light of any kind. Dark matter, the name given to this invisible component of the universe's mass, is one of the most important objects of study in modern cosmology, and its existence has been confirmed through multiple independent lines of evidence despite the fact that nobody has ever directly detected a dark matter particle in a laboratory. The first strong evidence for dark matter came from observations of galaxy rotation curves. In the 1970s, astronomer Vera Rubin and her colleague Kent Ford measured the speeds at which stars orbited the centers of spiral galaxies at different distances from the galactic center. According to Newtonian gravity, stars far from the center of a galaxy, where most of the visible mass is concentrated, should orbit more slowly than stars close to the center, just as outer planets in the solar system orbit more slowly than inner ones. This is what Rubin expected to find. What she found instead was that the rotation speed of stars and spiral galaxies does not decrease with distance from the center. It remains roughly constant, or even rises slightly far out into the galaxy's outer regions. This flat rotation curve is only explicable if there is a large amount of additional mass distributed throughout the galaxy in a roughly spherical halo extending well beyond the visible stars and gas. This invisible mass, not concentrated at the center like the stars, but spread throughout a large halo, was enough to explain the flat rotation curve. The ratio of dark matter to visible matter in typical galaxies is roughly 5:1. Since Rubin's work, dark matter has been confirmed through galaxy cluster dynamics, gravitational lensing observations in which the bending of background light reveals more mass than the visible matter can account for, the formation of large-scale cosmic structures, which requires dark matter to seed the gravitational collapse that formed galaxies, and the detailed structure of the cosmic microwave background, whose temperature fluctuations are affected by the gravitational influence of dark matter in the early universe. Dark matter is not a form of darkness in the poetic sense of the word. It is matter that is genuinely dark in the physical sense. It does not emit photons, does not absorb photons, does not scatter photons. It interacts with the rest of the universe only through gravity. It forms the invisible scaffolding on which the visible universe is built, the dark web of structure within which galaxies and galaxy clusters are embedded. The nature of dark matter particles remains unknown despite decades of intensive experimental effort. The most widely searched for candidate has been the weakly interacting massive particle, or WIMP, a class of particles predicted by supersymmetric extensions of the standard model of particle physics. WIMPs would have masses comparable to the proton, to the nucleus of a heavy element, would interact with ordinary matter only through the weak nuclear force and gravity, and would have been produced in the correct abundance in the early universe to account for the observed dark matter density. Decades of underground detector experiments, particle accelerator searches, and space-based indirect detection programs have searched for WIMPs without finding a confirmed signal. The Large Hadron Collider has explored the mass range where WIMPs were most expected and found nothing matching their predicted properties. Underground detectors like Xenon 1T and LX Zeppelin have pushed sensitivity to levels previously thought sufficient to detect WIMPs if they exist at natural abundance, without positive results. This has not eliminated WIMPs as a possibility, but has significantly constrained their properties. Alternative dark matter candidates include axions, light hypothetical particles originally proposed to solve a problem in quantum chromodynamics, which have their own dedicated experimental searches with some anomalous hints that have not been confirmed as definitive signals. Primordial black holes, formed from density fluctuations in the early universe, have been constrained by various observations, but remain viable over certain mass ranges. Sterile neutrinos, hypothetical heavier siblings of the standard model neutrinos, have also been searched for without confirmed detection. The persistence of the dark matter mystery, after 50 years of intensive effort, has led some researchers to propose modifications to gravity as an alternative, seeking to explain galaxy rotation curves and cluster dynamics without invoking dark matter particles. These alternative gravity theories, while successfully fitting some observations, have difficulty simultaneously explaining all the evidence that conventional dark matter models handle naturally, particularly the detailed structure of the CMB and the large-scale distribution of galaxies. In 1998, two independent teams of astronomers studying distant supernovae made a discovery that overturned one of the most fundamental assumptions in cosmology. They were looking at Type 1a supernovae, stellar explosions that can be used as standardizable candles to measure cosmic distances, and comparing those distances to the velocities at which the galaxies hosting the supernova were receding. The goal was to measure the deceleration of cosmic expansion to determine how much gravity was slowing the universe's expansion. What they found was that the distant supernovae were fainter than expected for their recession velocities. They were farther away than a decelerating or even coasting universe predicted. The expansion of the universe is not slowing down, it is speeding up. Something is driving the expansion to accelerate, and that something has been named dark energy. Dark energy, in the current standard model of cosmology, behaves like a constant energy density of empty space. As the universe expands and its volume increases, the amount of dark energy increases proportionally, maintaining a constant density per unit volume. This gives it a repulsive gravitational effect that grows as the universe gets larger. In the early universe, when the average density of matter was much higher, matter's gravitational attraction dominated and the expansion decelerated. But as the universe expanded and matter density diluted, dark energy's constant density began to win. And roughly 6 billion years ago, expansion began to accelerate rather than decelerate. The consequences for the darkness of space are profound. Accelerating expansion means that the cosmic horizon is continuously shrinking in terms of what we can ultimately reach. Galaxies currently just inside the observable universe that we could theoretically send a signal to are being carried away faster and faster. As time goes on, the number of galaxies within our causal reach decreases. In the far future, the only galaxies gravitationally bound to our local group will remain visible. All others will have been carried beyond the horizon by the accelerating expansion, their light redshifted to infinitely long wavelengths, permanently lost from any observation. Dark energy is therefore a driver of increasing darkness over cosmic time. It is expanding the black regions of space faster than any source of light can illuminate them, and it is doing so with accelerating speed. The darkness of space today is in some sense a preview of the profound darkness of the far future, when the universe's expansion will have carried nearly everything into permanent inaccessibility. The nature of dark energy is one of the deepest unsolved problems in all of physics. In the standard cosmological model, dark energy is described by a cosmological constant, a term Einstein originally introduced into his equations of general relativity in 1917 to produce a static universe, and then abandoned in 1929 when Hubble's discovery showed the universe was expanding. The irony of Einstein famously calling the cosmological constant his biggest blunder, only for later observations to require a non-zero cosmological constant to explain the accelerating expansion, is one of the more striking episodes in the history of physics. The cosmological constant has a precise physical interpretation in quantum field theory. It represents the energy density of empty space, often called vacuum energy. Quantum field theory predicts that empty space should be full of quantum fluctuations, pairs of particles and antiparticles briefly popping into existence and annihilating, contributing a net energy density to the vacuum. The problem is that the theoretically predicted vacuum energy density is anywhere from 60 to 120 orders of magnitude larger than the dark energy density actually observed. This discrepancy is sometimes called the worst prediction in physics, and understanding why the observed cosmological constant is so much smaller than the theoretical prediction is one of the central unsolved problems in theoretical physics. Recent observations have begun to test whether dark energy is truly constant, as the cosmological constant model predicts, or whether it varies with time in ways that would require a more complicated dynamical model. Results from the Dark Energy Spectroscopic Instrument, released in early 2024, showed hints that dark energy might not be perfectly constant, with the data showing slight preferences for models where dark energy evolves over cosmic time. These hints are not yet statistically conclusive, but they are motivating continued observation and theoretical work. If dark energy varies, it opens entirely new questions about the ultimate fate of the dark sky. The universe has not always contained the same number of stars producing light. Star formation, the process by which giant gas clouds collapse under gravity to form new stars, has followed a specific trajectory through cosmic history. And that trajectory explains a lot about why the sky is as dark as it is, rather than somewhat brighter. In the very early universe, before about 100 million years after the Big Bang, no stars existed at all. The universe was filled with hydrogen and helium gas, cooling and expanding from the initial hot, dense state, but not yet condensed into the compact objects needed for nuclear fusion. This is called the cosmic dark ages, and during this period, the universe was genuinely dark in every band of the electromagnetic spectrum, except for the cosmic microwave background itself. The first stars began forming roughly 100 million to 200 million years after the Big Bang. These first stars, called population 3 stars, were made entirely of hydrogen and helium, having formed before the first generation of supernovae had enriched the gas with heavier elements. They were extraordinarily massive by current standards, some hundreds of times the mass of the Sun, burning ferociously and dying quickly in supernova explosions that distributed the first heavy elements through the surrounding gas. These deaths seeded the conditions for the next generation of stars. Star formation then ramped up dramatically, reaching a peak around 3 to 4 billion years after the Big Bang, when the universe was between 1/4 and 1/3 its current age. During this cosmic noon, as it is sometimes called, the rate of star formation per unit volume of space was roughly 10 to 30 times higher than it is today. The universe was producing stars at a prodigious rate, and the resulting light output was correspondingly higher. Since that peak, the star formation rate has declined steadily. As gas is consumed by star formation and subsequent stellar evolution, the supply of available star-forming material decreases. Today, the universe forms stars at roughly 1/10 the rate it did at cosmic noon. The sky is dimmer than it was at the universe's peak brightness, and it will continue to dim as the remaining gas supply is exhausted over the coming trillions of years. The star formation history tells us that the universe was once brighter than it is now, and that it was not as bright as Olbers' infinite static universe would predict even at its brightest. The peak brightness, integrated over the full spectrum, was still many orders of magnitude below the infinite universe prediction. Because even at peak activity, the universe had a finite age, a finite number of stars, and an expanding space that redshifted the most distant light. The measurement of the star formation rate across cosmic time has been one of the major achievements of observational astronomy over the past 3 decades. By observing galaxies at different redshifts, and therefore different epochs in cosmic history, and measuring specific spectral signatures that indicate ongoing star formation, such as emission from ionized hydrogen and ultraviolet light from young massive stars, astronomers have constructed a detailed picture of how the rate of star formation has evolved from the universe's beginning to the present. The result, often displayed as what is called the Mado-Dickinson plot, after the astronomers who first compiled it in 1996, shows a clear rise from the first galaxies to a broad peak around redshifts of 2 to 3, corresponding to when the universe was between about 2 and 3 billion years old, followed by a continuous decline to the present day. The decline since the peak has been roughly a factor of 10 to 15 in the rate of new star formation per unit volume of space. The reasons for this decline are the subject of active research. One important factor is the gradual depletion of cold gas in galaxies, as successive generations of star formation consume the available fuel. Another is feedback from active galactic nuclei. The supermassive black holes at the centers of massive galaxies, when actively accreting material, drive powerful outflows that heat and expel the gas in the galaxy, shutting off further star formation. This AGN feedback mechanism is thought to be responsible for the striking observation that the most massive galaxies are often the reddest and oldest, their star formation having been quenched early by their central black holes. The implication for the brightness of the universe is straightforward. We live in a declining cosmic era in terms of star formation. The universe was a more vigorous light producer in the past than it is today. Future epochs will be progressively dimmer as the star formation rate continues to decline and the existing stellar population ages. One of the most important events in cosmic history, and one that is directly relevant to the darkness of space, is the moment when the universe first became transparent to light. In the very early universe, the conditions were such that photons could not travel any significant distance without being immediately absorbed and re-emitted. Light was trapped, unable to propagate freely. The universe was opaque in the same way that the interior of the sun is opaque, full of light, but light that couldn't go anywhere. From the Big Bang until about 380,000 years afterward, the universe was so hot and dense that matter existed as a plasma, a state in which the temperature is high enough to ionize atoms, stripping electrons from their nuclei. In this plasma state, free electrons scatter photons extremely efficiently, meaning any photon that starts traveling in one direction is quickly deflected in another direction by an electron collision. The mean free path of a photon, the average distance it travels before being scattered, was tiny. The universe was filled with light, but not transparent to it. The event that changed this was recombination, which occurred when the universe had expanded and cooled enough that electrons could combine with protons to form neutral hydrogen atoms. Neutral atoms are far less effective at scattering photons than free electrons, and when the universe transitioned from plasma to neutral gas over a period of tens of thousands of years, the mean free path of photons jumped from essentially zero to essentially infinite. Photons that had been trapped in the plasma were suddenly free to travel. These newly freed photons are precisely what we detect today as the cosmic microwave background. They have been traveling for about 13.4 billion years since they were released at recombination. They were emitted in all directions from every point in the universe at recombination, and they have been spreading outward ever since. The ones that were emitted from a spherical surface around our current location, at just the right distance that they have spent 13.4 billion years traveling to reach us now, are the ones we detect as the CMB. Before recombination, the universe was opaque, not just to visible light, but to all electromagnetic radiation. There is no light from that era that we can see, no matter how powerful our telescopes. The surface of last scattering at recombination is a literal wall beyond which no electromagnetic observation can penetrate. The universe has not always been transparent, and the transparency we now enjoy is itself a feature of the cooling and expansion that followed the Big Bang. The transition from opacity to transparency at recombination was not perfectly sharp. The hydrogen in the universe was not all neutral before recombination, and then all neutral afterward. The transition took place over a period of roughly 100,000 years, during which the fraction of neutral hydrogen increased progressively from 0 to nearly 100%. During this transition, the universe was translucent rather than fully transparent, allowing photons to travel somewhat, but with significant scattering. The surface of last scattering, the epoch from which the CMB photons were most recently scattered before traveling to us, corresponds to a redshift of about 1,100 in an age of the universe of about 380,000 years. This is not a sharp surface in reality, but a layer with some thickness corresponding to the duration of the recombination transition. The thickness of this surface can be measured through the angular damping of CMB fluctuations at small scales, and it provides information about the physics of recombination and the expansion history of the universe. After recombination, the universe entered a period called the Cosmic Dark Ages, from about 380,000 years to perhaps 200 to 300 million years after the Big Bang. During this epoch, the universe was filled with neutral hydrogen and helium gas, expanding and cooling but containing no sources of light, no stars, no galaxies, no active galactic nuclei. This is the only epoch in the universe's history that was truly dark in every wavelength, not just the visible. The only radiation was the cooling remnant of the CMB, and the small amount of residual radiation from the processes of recombination itself. the first stars ended the cosmic dark ages by producing ultraviolet radiation that rionized the surrounding hydrogen gas. This epoch of rionization is one of the most important transitions in cosmic history, and one that astronomers are now studying with instruments designed specifically to detect the signature of neutral hydrogen in the early universe. The distribution of matter in the universe is not uniform. On the largest scales, galaxies are organized into a vast three-dimensional network called the cosmic web, consisting of dense filaments of matter connecting galaxy clusters at their nodes, surrounding enormous empty voids that contain very little matter at all. This web-like structure, revealed by large-scale galaxy surveys over the past 4 decades, is the result of small density fluctuations in the early universe being amplified by gravity over billions of years. The cosmic web has implications for how light moves through the universe and how the darkness is distributed. In the dense regions within galaxy clusters and along filaments, light from the many galaxies and hot gas must travel through an environment that has various effects on it. Hot gas in galaxy clusters scatters photons from the cosmic microwave background, slightly distorting the CMB pattern in a way called the Sunyaev-Zeldovich effect. Gravitational lensing by the mass concentrated in clusters and filaments bends light paths, distorting and sometimes magnifying the images of background galaxies. In the enormous voids, which occupy perhaps 80% of the universe's volume by some estimates, conditions are very different from the filaments and clusters. The matter density in voids is far below the cosmic average. Photons traveling through voids experience almost no absorption or scattering from intervening matter. They travel in nearly perfect straight lines through essentially empty space. If you are located at the center of a void, the darkness around you is particularly profound. The nearest galaxies may be tens of millions of light years away in every direction. The intergalactic medium, the gas that fills the space between galaxies throughout the cosmic web, has been important at various stages of cosmic history. After recombination, the neutral hydrogen that filled the universe gradually became ionized again as the first stars and quasars produced ultraviolet radiation in a process called cosmic reionization that occurred over the first billion years after the Big Bang. This reionization changed the intergalactic medium from neutral gas, which absorbs ultraviolet light strongly, to ionized gas, which is far more transparent. The transparency of the present-day intergalactic medium to most wavelengths of light is part of why we can see galaxies at extreme distances at all. The detailed mapping of the cosmic web has been accomplished through large spectroscopic galaxy surveys that measure the positions and velocities of millions of galaxies in 3 dimensions. The Sloan Digital Sky Survey, the 2DF Galaxy Redshift Survey, and more recently, the Dark Energy Spectroscopic Instrument have produced the most detailed 3-dimensional maps of the universe ever made, revealing the web's filamentary structure, the locations of galaxy clusters at the intersections of filaments, and the dimensions and distribution of the voids. The voids are among the most striking features of the cosmic web. The Biada's void, discovered in 1981, is one of the most prominent, stretching roughly 250 million light-years in diameter. Few galaxies occupy its interior, leaving a nearly spherical region of relative emptiness in the galaxy distribution. Voids of this scale are predicted by simulations of structure formation beginning from the CMB initial conditions, and their existence is a confirmation that the standard cosmological model correctly describes how gravity amplifies small early universe density fluctuations into the large-scale structures observed today. Light from a source within a void follows a different path through the universe than light from a source embedded in a galaxy cluster. Within the void, there are few absorbers, few scatterers, and the photons travel in nearly perfect straight lines. The low matter density means gravitational lensing effects are minimal. In contrast, light passing through a massive cluster is deflected significantly, and in extreme cases produces the dramatic gravitationally lensed arcs and multiple images of background galaxies visible in deep cluster images. The cosmic web also plays a role in the distribution of what is called the diffuse extragalactic background light, the total accumulated light from all galaxies throughout cosmic history, integrated over all frequencies. This background, measurable in principle though difficult to isolate from local foregrounds, encodes the complete history of light production in the observable universe. Measurements of this background provide constraints on the total star formation history and the distribution of galaxy types across cosmic time. One of the most precise uses of the cosmic web structure as a cosmological tool is the phenomenon of baryon acoustic oscillations, or BAO. In the early universe, the coupled plasma of photons and baryons supported pressure waves, sound waves that propagated through the plasma. At recombination, these waves were frozen in place, leaving a characteristic scale imprinted in the distribution of matter. This scale, roughly 500 million light-years in the present universe, acts as a standard ruler that can be measured in galaxy surveys at different redshifts. By measuring how this scale appears to change with redshift, astronomers can trace the expansion history of the universe with remarkable precision, providing constraints on dark energy that complement those from supernovae and the CMB. Space is dark, partly because some of the light produced throughout cosmic history has been permanently removed from the universe's photon inventory by black holes. A black hole is a region of space-time where gravity is so intense that nothing, including light, can escape once it has passed the event horizon. Every photon that falls into a black hole is gone from the observable universe, contributing nothing to the sky brightness and never arriving at any observer's detector. The universe contains black holes over an enormous range of masses. Stellar mass black holes, formed when massive stars exhaust their nuclear fuel and collapse, range from a few solar masses to perhaps 100 or more. These are distributed throughout galaxies in the millions to billions. Intermediate mass black holes of hundreds to thousands of solar masses may populate the centers of smaller galaxies and globular clusters. Supermassive black holes at the centers of most large galaxies range from millions to billions of solar masses. The supermassive black holes are particularly relevant to the light budget of the universe, not primarily because they are eating photons today, but because of their profound effect on the history of galactic evolution and star formation. When a supermassive black hole is actively accreting material, it becomes what is called an active galactic nucleus, or quasar, and it releases enormous amounts of energy, far more than the galaxy's stars combined. But it also drives powerful jets and winds that heat the surrounding gas, suppressing star formation in the host galaxy, and reducing the number of stars that form over time. The most massive black holes in the universe today contain matter equivalent to billions of solar masses. This matter, which could in principle have formed stars, instead sits in a gravitational singularity emitting no light of its own and contributing only to the total mass of the galaxy. The photons that fell into those black holes during the quasar era are gone permanently. They have been removed from the universe's light inventory, absorbed into singularities from which no information can escape. Hawking radiation, the quantum mechanical process by which black holes slowly lose mass through thermal radiation, is far too faint to be observationally relevant for astrophysical black holes on any human timescale. For a stellar mass black hole, the Hawking temperature is so far below the temperature of the cosmic microwave background that the black hole actually absorbs more energy from the CMB than it radiates. These black holes are truly dark for the foreseeable future of the universe. The era of quasars, which peaked at redshifts between 2 and 3 when the universe was a few billion years old, was the most energetically active period in the universe's history from the perspective of supermassive black hole accretion. During this era, Black holes at the centers of galaxies were consuming material at prodigious rates, producing luminosities thousands of times brighter than the entire Milky Way from their tiny accretion zones. The energy released, while enormous, also provided the feedback that eventually shut down their own growth by heating and expelling the gas supply. The quasar era produced a substantial contribution to the extragalactic background light, specifically in the X-ray and extreme ultraviolet ranges where accretion onto black holes is most luminous. This background, called the cosmic X-ray background, was discovered in 1962 by Riccardo Giacconi, who received the Nobel Prize for this and related work. The cosmic X-ray background was eventually shown to be the summed emission of millions of active galactic nuclei at various redshifts, integrated along our line of sight through cosmic history. The role of black holes in setting the large-scale structure of the universe, through their feedback effects on galaxy formation, means they indirectly affect the distribution of all light in the universe. Galaxies in which black hole feedback quenched star formation early became the red, passively evolving elliptical galaxies that dominate the most massive end of the galaxy mass function today. These galaxies, once among the brightest objects in the universe during their quasar phase, now shine only with the fading light of their aging stellar populations. The black hole at the center of each, having shut down its own fuel supply, sits dormant and dark, waiting for a future source of material. The night sky has changed throughout cosmic history and will continue to change in the future. Understanding where the universe is heading illuminates what our current night sky represents in the full context of cosmic time, and the prognosis for cosmic brightness is, in a word, grim. As dark energy continues to accelerate the universe's expansion, the redshift of distant galaxies increases. Galaxies currently visible in the far ultraviolet will be redshifted to the far infrared. Galaxies currently visible in the infrared will be shifted to the microwave. Eventually, even the most nearby galaxies beyond our local group will cross the cosmic event horizon, their light redshifted to infinitely long wavelengths, undetectable by any physical instrument. The local group of galaxies, gravitationally bound together, will survive this expansion. The Milky Way and Andromeda are currently approaching each other and will merge in roughly 4.5 billion years, forming a large elliptical galaxy sometimes called Milkomeda. The other members of the local group will eventually merge into this structure as well. In the far future, the only galaxies visible from anywhere in what was once our local group will be the merged remnant of the local group itself, surrounded by perfect darkness in every direction. Even within this merged galaxy, the stellar population will age. Stars consume their fuel and die, and the rate of new star formation decreases as the available gas supply is consumed. Over hundreds of billions of years, the most massive and luminous stars will burn out first, followed by progressively less luminous stars. The galaxy will redden and dim as its stellar population evolves toward the faint, slowly cooling remnants called white dwarfs, neutron stars, and black holes. Estimates of the timescale for the last stars to burn out vary, but the most persistent stellar objects, the smallest red dwarf stars, may burn for as long as 10 trillion to 100 trillion years. Even that is a finite time. Eventually, every star that will ever form will have exhausted its fuel. The universe will be a cold, dark collection of stellar remnants, slowly losing their residual heat to an expanding void. The timescale for the complete darkening of the universe beyond our local group is surprisingly not that long on cosmological scales. Within the next 100 billion years, essentially all galaxies beyond our local group will have been carried beyond the event horizon by the accelerating expansion. The local supercluster, including the Virgo cluster and its associated galaxies, will drift beyond reach within a few tens of billions of years. The Milky Way's nearest large extragalactic neighbors beyond our bound local group are already receding faster than they are approaching. Future observers in 100 billion years, assuming they exist, will see a universe that looks profoundly different from ours. The sky will contain only the remnants of the local group merged into a single giant elliptical galaxy, surrounded by blackness in every direction. No distant galaxies will be visible. The cosmic microwave background will have cooled to temperatures so low that even the most sensitive future detector would struggle to find it. The universe will appear to contain nothing beyond the local gravitational island. These observers will face a profound epistemological challenge. From their observational evidence alone, they will have no way to reconstruct the rich cosmological history that we can currently observe. They will see an old galaxy surrounded by darkness, and will have no direct evidence that the universe was ever anything other than this one galaxy. The accelerating expansion will have erased the observational evidence for the Big Bang itself. Our cosmic generation has the unique privilege of observing a universe still young enough to contain its own history, still small enough in its expansion that the evidence of its origin is visible in every direction we look. The star formation decline also affects the spectral character of the universe's light output over time. Young, hot, massive stars produce primarily blue and ultraviolet light. As these massive stars die off in the first few billion years of a galaxy's life and are not replaced at the same rate, the stellar population ages and reddens. The universe was bluer in the past than it is now, and it will be redder in the future as the massive stellar population continues to thin. The integrated color of the universe, average over all its galaxies, has been measurably reddening over cosmic time, a trend that will continue until the last cool red stars burn out. The future universe, before it goes completely dark, will be a deep red universe rather than the blue-white universe that astronomers of 2 to 3 billion years ago would have observed. The darkness of the night sky is not just an observation waiting for explanation. It is evidence, active, positive evidence for a specific cosmological model that includes a universe of finite age that began in a state of extremely high temperature and density and has been expanding ever since. This evidence precedes the detailed quantitative formulation of the Big Bang model, and had cosmologists of earlier eras thought carefully about what they were observing, they might have deduced the Big Bang from the darkness of the sky before they had the observational and theoretical tools to confirm it independently. The argument runs as follows. If the universe were infinitely old, static, and infinite in extent, every line of sight would eventually hit a stellar surface, and the sky would be blazing bright as previously described. The sky is not blazing bright. Therefore, at least one of those premises is wrong. Either the universe is finite in extent, which creates its own problems about what lies beyond the boundary, or the universe has a finite age, meaning stars have not been shining forever, or the universe is not static, meaning its expansion is redshifting distant light out of the visible, or some combination of these. Modern cosmology has determined that all three of the alternatives are simultaneously true in important senses. The observable universe is finite in extent, limited by our particle horizon. The universe has a finite age of about 13.8 billion years, so stars have been producing light for at most that long, and the universe is expanding, redshifting light from distant sources. The darkness of the sky is the observable fingerprint of all three facts simultaneously. The cosmic microwave background, as discussed earlier, is the direct observational confirmation of the Big Bang. Its existence, its temperature, its spectrum, matching a perfect blackbody at 2.725 Kelvin, and its tiny but precisely measured temperature and isotropies all confirm the standard cosmological model with extraordinary precision. But that model was already implied by Olbers' paradox, waiting to be deduced from the simple fact that the night sky is dark rather than bright. The deduction of the Big Bang from the darkness of the night sky is an example of what physicists call reasoning from negative evidence. The sky being dark is a negative observation. It is the absence of something that should be present under one model. But negative observations can be enormously informative. And in this case, the absence of the sky brightness predicted by the infinite static universe model rules out that model and points toward its alternatives. The power of Olbers Paradox is that it is sensitive to the large-scale structure of the universe in a way that direct observation of individual objects is not. Any single observation of a galaxy or a star tells you about that specific object and its local environment. But the darkness of the sky tells you something about the universe as a whole, its age, its dynamics, the integrated history of light production across all sources and all time. It is a global constraint in a way that local observations are not. The quantitative match between the observed sky brightness and the Big Bang model's prediction is part of what makes the CMB discovery so powerful. The model predicts not just that there should be a background radiation, but that it should have a specific temperature and a specific spectrum. The measured temperature of 2.725 Kelvin and the perfect blackbody spectrum of the CMB match the model's predictions. The tiny temperature fluctuations in the CMB at the level of 1 part in 100,000 match the statistical pattern predicted from the initial conditions of inflation. The darkness of the visible sky and the existence of the microwave background are together a two-part confirmation of the Big Bang that no alternative cosmological model has successfully reproduced. The argument from Olbers' paradox to the Big Bang can be formalized. If we observe that the total sky brightness in visible light is many orders of magnitude below the prediction of an infinite static universe, and if we can rule out absorption as an explanation because absorbers would heat up and re-radiate, then we need a model where either the number of stars is finite or their average age is finite or their light is somehow suppressed. All three of these are features of the Big Bang model. The universe has a finite age, and therefore stellar lifetimes are bounded. There are a finite number of stars within any accessible volume, and the expansion of space redshifts light from distant stars into invisible wavelengths. No other known cosmological model provides all three effects simultaneously in a way that matches quantitative observation. Every photon that enters your eye on a dark night has been traveling for some portion of the age of the universe. The darkness between the stars is not simply empty space. It is filled with photons in transit, most of them invisible to naked eye observers, all of them carrying information about the sources that emitted them and the space they have crossed. The light from the nearest star visible to the naked eye, Alpha Centauri, is about 4.37 years old when it reaches you. The light from Sirius, the brightest star in the night sky, set out about 8.6 years ago. The light from Deneb, a bright star in Cygnus, is between 1,400 and 2,600 years old, depending on which distance measurement you use, meaning the light you see when you look at Deneb was emitted during or before the Roman Empire. The Andromeda galaxy, visible to the naked eye as a faint smear of light in a dark sky, shows us what Andromeda looked like about 2.5 million years ago, before our genus Homo had even appeared on Earth. The most distant objects visible in large telescope images, galaxies at redshifts above 10, show us the universe as it was when it was less than 500 million years old, less than 4% of its current age. These are infant galaxies, irregular and turbulent, lacking the orderly structure of mature spirals like the Milky Way. They are patches of light that have been traveling toward us for over 13 billion years. Photons that were emitted when the universe contained none of the heavy elements that make up most of the matter in your body. Photons that have crossed a substantial fraction of the observable universe to reach your telescope. The darkness between these points is the darkness between different moments in time, as much as it is the darkness between different locations in space. The sky is a four-dimensional structure, and every dark region between the lights is a region where the photons that would have illuminated it have either not yet arrived or have been stretched by expansion into invisibility. The darkness has depth, temporal depth. And reading it correctly requires thinking not just about where things are, but about when things happened. The concept of look-back time is fundamental to how astronomers interpret their observations. When we observe an object at a redshift of 1, meaning its light wavelengths have been stretched to twice their emitted values, we are seeing that object as it was about 8 billion years ago, when the universe was roughly half its current age. The object we observe today might be very different from what we see. It may have undergone mergers, may have lost or gained a quasar phase, may have changed its morphology from irregular to elliptical. The power of large photometric and spectroscopic surveys is that they provide snapshots of the universe at many different look-back times simultaneously. A single deep field image, like the original Hubble Deep Field taken in 1995, contains galaxies at a vast range of distances, and therefore a vast range of look-back times, from nearby galaxies observable as they were a few 100 million years ago, to the faintest specks representing galaxies as they were more than 13 billion years ago. The image is literally a cross-section through cosmic time, a fossil record of galaxy evolution laid out in the third dimension of distance. The James Webb Space Telescope has extended this capability dramatically, observing galaxies at redshifts above 13, corresponding to when the universe was less than 400 million years old, less than 3% of its current age. The galaxies found at these extreme distances are among the most massive and brightest objects expected at that epoch, a distribution that has surprised some theoretical predictions and is driving revisions to models of early galaxy formation. The night sky continues to be a source of information about cosmic history at every level of technological sophistication we bring to studying it. The technology of astronomical observation has continuously pushed the time machine analogy further. Each new generation of telescope has accessed progressively higher redshifts, earlier cosmic epochs, more ancient light. The Hubble Space Telescope, with its sensitivity and its location above the atmosphere's distorting effects, opened up redshifts above 5 in a way that ground-based telescopes could not. The James Webb Space Telescope has pushed routinely into the domain of redshifts above 10, observing galaxies that formed within the first few 100 million years of the universe's existence. The Square Kilometer Array, currently under construction, will detect radio emission from neutral hydrogen in the epoch of reionization, hearing the universe before it fully switched on its first lights. The most profound darkness in the observable universe is found not between stars within galaxies, but in the enormous voids between galaxies and galaxy clusters. These regions, which make up the majority of the universe's volume, contain densities of matter 100 times lower than the cosmic average. A typical intergalactic void might extend for 50 to 100 million light-years in diameter, containing almost no galaxies within its interior. The darkness within a void is qualitatively different from the darkness of a clear night sky on Earth. On Earth, even on the clearest night, you are surrounded by the atmosphere, by the glow of distant cities, by the Milky Way itself, by the zodiacal light from interplanetary dust, and by thousands of visible stars and dozens of visible galaxies. The total darkness of a true intergalactic void would exceed anything achievable within our galaxy. But the void is not empty in the physicist's sense. It contains diffuse gas, though at extremely low density. It contains the cosmic microwave background, which fills all of space uniformly. It contains dark matter halos, tenuous but present, that will eventually gravitationally attract more matter and perhaps seed future galaxy formation. It contains cosmic rays, energetic charged particles that travel through the intergalactic medium without significant deflection. And it contains gravitational waves, ripples in space-time produced by merging black holes and neutron stars throughout cosmic history, propagating through the void at the speed of light. The darkness of the void is a physical state with measurable properties. not simply the absence of everything. The cosmic background fills it. The gravitational influence of surrounding structure shapes it. The rare photon crossing it from a distant source is subject to gravitational lensing by the dark matter halos within it. To call the void dark is correct only if dark means transparent to visible light and sparse in visible light-emitting matter. In every other physical sense, the void is active, filled, and measurable. The intergalactic medium within galaxy clusters, where hot X-ray emitting gas fills the space between member galaxies, is a distinct environment from the cooler, more diffuse gas in voids. Clusters contain gas heated to temperatures of tens of millions of Kelvin by gravitational infall and by energy input from active galactic nuclei. This gas is so hot that it radiates primarily in X-rays. Despite being hot and emitting light, this gas is not visible to the naked eye and contributes only to the X-ray sky rather than the visible sky. The observation of this hot cluster gas provides important cosmological information. The ratio of gas mass to total mass in clusters, measured through X-ray observations combined with mass estimates from gravitational lensing, constrains the ratio of baryonic to total matter in the universe. The evolution of cluster populations with redshift, the way the number of clusters of a given mass changes with cosmic time, constrains the growth of cosmic structure and the properties of dark energy. Clusters are therefore powerful cosmological probes whose study illuminates both the darkness between their member galaxies and the broader cosmological context in which they exist. The warm, hot intergalactic medium, a diffuse gas component at temperatures between 100,000 and 10 million Kelvin, occupying the cosmic filaments of the web between clusters, is thought to contain a substantial fraction of all the ordinary matter in the universe at low redshift. This gas has been difficult to observe because it is too cool to emit strongly in X-rays, but too hot to be detected in neutral hydrogen radio surveys. It may be responsible for a long-standing puzzle in cosmology called the missing baryon problem, where only about half the ordinary matter predicted by Big Bang nucleosynthesis and confirmed by the CMB can be found in observed structures. The measurement of the total integrated background light from all galaxies, called the extragalactic background light, or EBL, has been a challenging observational goal because it requires separating the faint, cosmological signal from much brighter local foregrounds, including the zodiacal light from dust in the solar system, diffuse emission from the Milky Way, and instrumental effects. The New Horizons spacecraft, which travel beyond the inner solar system, where zodiacal light is much fainter, has provided measurements of the optical EBL from its vantage point in the outer solar system. These measurements have helped constrain the total star formation history of the universe by independently measuring how much light all galaxies have produced over cosmic time. The EBL also absorbs high-energy photons from distant sources through a process called pair production, in which a high-energy gamma-ray photon interacts with a lower-energy EBL photon to produce an electron-positron pair. This process makes the universe increasingly opaque to very high-energy gamma rays from distant sources, and the scale of this attenuation, measurable by comparing the observed spectra of distant blazars with their predicted intrinsic spectra, provides an independent measurement of the EBL intensity and therefore of the integrated star formation history. It is worth spending some time imagining what an observer in Olbers Paradox universe, the infinite static, uniformly stellar universe, would actually experience, because the predicted brightness is so extreme that its consequences go far beyond a merely brightly lit sky. In a universe where every line of sight terminates on a stellar surface, the entire sky, every square degree of it, would glow at the surface temperature of a typical star, roughly 5,000 to 6,000 Kelvin for a sun-like star. The The brightness of such a sky would be comparable to the brightness of the surface of the sun. Not the brightness of sunlight on Earth, which has been diluted by distance, but the actual surface brightness of the solar photosphere. The total flux of radiation hitting any object in such a universe from all directions simultaneously would be staggering. Every square meter of any surface would receive radiation equivalent to what the sun's surface receives from below. The equilibrium temperature that any object would reach in this radiation field would be comparable to the surface temperature of a star, roughly 5,000 to 6,000 Kelvin. At this temperature, rock melts. At this temperature, water does not exist as a liquid. At this temperature, complex molecules are dissociated. At this temperature, the chemistry of life is impossible. In a universe with a truly bright night sky satisfying Olbers' prediction, no planet could have liquid water. No atmosphere could have the chemical complexity of Earth's. No surface could harbor life as we know it. The darkness of the night sky is not just an aesthetic feature of the universe. It is a necessary condition for the kind of temperate, chemically complex environments in which complex chemistry and life can exist. The specific darkness of our sky, a small number of bright points against a dark background, is what allows planets at the right distance from a single star to be much colder than stellar surfaces, to have temperatures in the range where water is liquid, where organic chemistry is stable, where the complex molecular machinery of life can operate. We exist in the darkness between the stars, and the darkness is not our enemy. The darkness is a prerequisite for our existence. The argument for why a bright sky precludes life goes beyond surface temperature effects to the chemistry of complex molecules. Organic molecules, the building blocks of biochemistry, are held together by relatively weak chemical bonds involving electron sharing between atoms. At temperatures of several thousand Kelvin, the thermal energy available to any given molecule far exceeds the binding energy of these bonds. Carbon-hydrogen bonds, carbon-carbon bonds, and the other linkages that make up the backbone of biochemistry would be continuously broken, and the resulting fragments would be unable to recombine into stable, complex structures. Even simpler chemistry is affected. Water, at the surface temperatures of a star, does not exist as a liquid or even as a stable molecule. The hydrogen and oxygen dissociate into atomic gas. The chemistry that drives Earth's geological cycles, the dissolving of minerals in water, the precipitation of carbonates, the cycling of nutrients through the biosphere, all of this requires liquid water as a solvent and would be absent in a world at stellar surface temperatures. The darkness of the space between stars is what makes the existence of planets with moderate temperatures possible at all. A planet at Earth's distance from the Sun receives energy from one direction only, from the Sun itself, and can radiate that energy away in all other directions, into the cold dark of space. This one-directional heating balanced by omnidirectional cooling is what establishes Earth's temperature around 288 Kelvin. In a uniformly bright sky at stellar surface temperatures, there is no cold dark to radiate heat into. The thermodynamic gradient that allows planets to have temperatures far below stellar photospheres would not exist. The darkness is not background scenery. It is an active participant in making life possible. There is a closely related observation about the role of darkness in biological evolution. The presence of a light-dark cycle driven by Earth's rotation and the Sun's directionality, combined with the darkness of the surrounding sky that allows the planet to radiate heat and maintain moderate temperatures, was a constant feature of the evolutionary environment of all Earth's life. Organisms evolved to exploit both the light hours for photosynthesis and visual navigation, and the dark hours for sleep, navigation by stars, and other activities that require low-light conditions. The structure of the human brain and sleep cycle is tuned to a world where the sky is dark at night. The darkness is not just permitting life by allowing moderate temperatures. It is woven into the biology of the life that evolved within it. The observable universe is the region of space from which light has had time to reach us in 13.8 billion years. Beyond it lies the rest of the universe, unknown and perhaps unknowable, but not necessarily absent. Current inflationary cosmology, the theoretical framework describing what happened in the first tiny fraction of a second after the Big Bang, predicts that the total extent of space created during inflation is vastly larger than the observable portion, perhaps by a factor of 10 to the power of 10 to the power of 50 or more, a number so far beyond intuition that it might as well be described as infinite. In this broader universe beyond our horizon, stars almost certainly exist in similar abundance to what we observe within our observable patch. Since the cosmological principle, the assumption that the universe is roughly the same everywhere on large scales, is supported by everything we can observe. Those stars are producing light, but that light will never reach us, not because of any temporal limitation, but because the accelerating expansion of the universe has permanently separated us from those regions. Light they emitted long ago is racing toward us, but the space between us is expanding faster, an ever-growing gap that no photon can bridge. The darkness that faces us in the direction of the unobservable universe is therefore a particular kind of darkness, the darkness of permanent causal separation. It is as if those regions were on the other side of a horizon from which nothing can return, analogous to the event horizon of a black hole, but operating at the scale of the universe itself. The light from those regions will never arrive because the universe will not permit it, not through any absorbing medium or redshift to invisibility, but through the pure geometry of an expanding space-time that separates us from them irreversibly. This is a humbling fact. The observable universe, with its 2 trillion galaxies and its billions of years of history, is only a tiny fraction of everything that exists. We sit in a cosmic bubble of the observable, surrounded by an unimaginable expanse of space that is forever dark to us, not because it is empty, but because the light from it can never reach us. The darkness at the edge of our observational reach is the darkness of permanent separation from most of what the universe contains. Inflationary cosmology, the theory developed in the early 1980s by Alan Guth and subsequently refined by Andrei Linde, Alexei Starobinsky, and others, predicts that the universe underwent a period of exponentially rapid expansion in its first tiny fraction of a second, growing by perhaps 60 or more e-foldings in scale, meaning it increased in size by a factor of e to the power of 60, which is an incomprehensibly large number. This inflation stretched quantum fluctuations to macroscopic scales, seeding the density perturbations that grew into cosmic structure, and potentially created a universe vastly larger than the observable patch we can see. In some versions of inflation, the rapid expansion continues eternally in regions beyond our observable universe, a concept called eternal inflation. In this picture, what we call the universe is just one bubble that stopped inflating, while inflation continues around and beyond it, creating other bubbles with potentially different physical laws or constants. These other bubbles, if they exist, are separated from us by exponentially large distances, forever beyond any possible observation. This is the multiverse, and it represents the ultimate dark in the sense of the permanently unobservable. Whether the multiverse is physics or metaphysics is a question that honest physicists disagree about. Inflation does predict eternal inflation under fairly general conditions, and eternal inflation does predict the generation of bubble universes beyond our horizon. But since those bubbles are by construction unobservable, no experimental test can confirm or deny their existence. What we can say is that if the multiverse is real, we are surrounded by a vastness that makes even the 2 trillion galaxy observable universe look tiny. And the darkness of our observable horizon is not the edge of existence, but merely the edge of our causal reach. The current best understanding is that the observable universe despite being the largest structure we can probe, is not likely to be representative of all that exists. The flatness of the universe, observed to high precision by CMB measurements, implies that the universe is at least on the order of 100 to 1,000 times the size of the observable sphere. Some inflationary models predict sizes of 10 to the 100th power times the observable universe or larger. Whatever lies beyond is presumably similar in broad statistical properties to what we observe within our bubble, because the cosmological principle should apply on all accessible scales. But the specific content, the specific arrangement of galaxies and voids and structures, is unique and will never be known to us. The question, why is space dark, has an answer that took centuries to complete and that required some of the greatest scientific advances of the modern era. The full answer combines the finite age of the universe, which limits how long starlight has been accumulating, the expansion of space, which redshifts the light from distant stars into invisible wavelengths, the finite speed of light, which means we can only see stars whose light has had time to reach us, and the accelerating expansion driven by dark energy, which ensures that more and more of the universe becomes permanently invisible over time. But the darkness of space is not just the answer to an old puzzle. It is itself a profound message about the nature of the universe we inhabit. The darkness tells us the universe had a beginning. It tells us the universe is expanding. It tells us that expansion is accelerating. It tells us there is more to the universe than we can see. And it tells us that the specific conditions that allow us to exist, the cold, dark gaps between the stars, where temperatures allow water to be liquid and molecules to be stable, are themselves a consequence of the cosmological history that the darkness encodes. There is a humbling and clarifying quality to looking up at a dark sky and understanding what you are actually seeing. The darkness is not emptiness. It is a record. It is filled with photons in transit from distant sources, arriving with information about the state of the universe billions of years ago. It is filled with the cosmic microwave background, the cooled remnant of the universe's earliest accessible light. It is filled with gravitational waves from violent events across cosmic history. It is shaped by dark matter that we cannot see, and dark energy that is expanding the void between every visible point. The darkness is, in the deepest sense, the universe being honest with us about its age, its history, and its limitations. We exist in a window of time when the sky is dark but still full of visible light from billions of galaxies. In the far future, the accelerating expansion will have emptied the visible sky of everything beyond our local gravitationally bound cluster. And future observers, if any exist, will look out at a sky darker than ours and will have no way from their observations to deduce the rich cosmic history that we have been fortunate enough to glimpse. We live in a dark universe, but we live in the right kind of dark, in the right kind of place, at the right kind of time, to have worked out why. The specific answer to why space is dark is ultimately a story about the limits of the observable. The universe is extraordinarily generous with its light, producing it from hundreds of billions of galaxies containing trillions of stars each, all burning through their nuclear fuel and radiating photons in all directions for billions of years. There is no shortage of light being produced. The darkness comes from the conversion of that light into forms we cannot see, through the redshift of expansion, and from the finite time that light has had to reach us across the immensity of space. Understanding the darkness is understanding something fundamental about the relationship between the observer and the universe. We exist at a specific location in space at a specific moment in time, with specific observational capabilities, and everything we know about the cosmos is filtered through those specificities. The darkness we see is the darkness relevant to our location, our epoch, and our biology. A different kind of observer at a different time would see a different sky, literally different in its brightness and structure, depending on when they lived in cosmic time. There is a kind of epistemic humility required when looking at the dark sky and understanding what it represents. It is not the full universe. It is the universe as accessible from here, now, through eyes that evolved on a single planet around a single star. The total universe is incomprehensibly larger. The total electromagnetic output of all its light sources across all wavelengths, across all of history, is incomprehensibly greater than what our visible sky shows. And yet, the visible sky, dark as it is between its scattered points of light, contains within that darkness the story of the universe from its beginning to now. We live in a dark universe. That darkness is a message. The message is that the universe is finite in age, expanding in extent, and accelerating in that expansion. Reading the darkness correctly took most of human history to accomplish. Understanding what it says is one of the great achievements of the human mind.